friends, welcome back to my channel Physics DDTC. Today I come back with a new video of electrostatics, and today's discussion is about capacitance and capacitor. First we have to know what is capacitance. You know that capacitance is the capacity of storing some entity. In this case, in our chapter in electrostatics, we define capacitance is the capacity of storing charge by a conductor, and capacitor is the device which can store electrical charge. What happens here? We know that this is a conductor. If we give some charge in this conductor, then its potential will increase. And say this is the charge Q, and in this time the potential is V. Now if we give further charge, then we see that potential further increases. So we can say the charge Q is proportional to V, that is electric potential of the conductor. Now Q equal to some constant into V, and we take this constant C. Q equal to C V. The proportionality constant C is called capacitance. Capacitance of the conductor. Then, if we define C, then C equal to Q by V. Q by V, this is the capacitance. Then numerically, how we define the capacitance C? Here C is the capacitance. We can define capacitance is the required charge to increase its potential by unit. How? If V equal to 1, then we see that the capacitance C equal to Q. That is capacitance equal to charge. What amount of charge? This is the charge to increase its potential by unity. This is the capacitance. Okay. Now we discuss the factors on which the capacitance of a conductor depends. Factor. Number 1, size of the conductor. Size and also shape. The capacitance, that is capacity of storing charge, depends on size and shape of the conductor. Number 2, medium. And the medium is denoted by dielectric constant. In which medium the conductor is placed, this medium is responsible for the capacity or capacitance of the conductor. Number 3, nearby conductors or charged body. If near a conductor there is another charged body or another conductor, then the capacitance of the given conductor will change. These are some factors which governs the capacitance of a conductor. Now we see the unit of capacitance. First, CGS. This is stat farad. And number 2 is I. This is farad. Stat farad and farad. We can define what is 1 farad and what is 1 stat farad from the relation C equal to Q by V. First we define what is 1 farad. What is 1 farad? That if Q equal to 1 coulomb and V potential equal to 1 volt, then the capacitance of a capacitor is called 1 farad. That is 1 farad is the capacitance and it is the 1 coulomb charge required to raise its potential 1 volt. Then how to define 1 farad? 1 farad capacitance is the 1 coulomb charge. It's numerically equal to 1 coulomb charge required to raise its potential by 1 volt. Then 1 farad equal to 1 coulomb by 1 volt. And similarly, 1 stat farad equal to 1 stat coulomb by 1 stat volt or ESU potential. Stat volt. Okay? This is our CGS and SI unit of capacitance. CGS unit stat farad and SI unit farad. Now we derive the relation between stat farad and farad. Relation between stat farad and farad. First we write 1 farad. What is the definition of 1 farad? We already define 1 farad equal to 1 coulomb by 1 volt. Now 1 coulomb equal to 3 into 10 to the power 9 PSU charge, and 1 volt equal to 1 by 300 PSU potential. Then 1 farad equal to 3 into 3, 9 into 10 to the power 11 stat farad. Then we see 1 farad equal to 9 into 10 to the power 11 stat farad. This is our required relation between step farad and farad. We have already mentioned what is capacitor. Capacitor is a device which can store charge. Now, how to make different types of capacitor? First, we say about one type of capacitor, that is called parallel plate capacitor. Parallel plate capacitor. What is parallel plate capacitor? Parallel plate capacitor. A parallel plate capacitor consists of two parallel plates separated by a distance. Say this is B, and the space between two parallel plates is filled with some dielectric medium. Say this is K, dielectric constant K. Now one plate is charged with positive charge and the other plate is connected with R. If we connect with a positive charge source, then we get here positive charge, and by induction here we get minus charge, and in this surface we get some plus charge. As the plate is connected with earth, this plus charge will be neutralized by the electron flow of electron from earth. Thus the only remaining charge here in this plate, only the charge is negative charge. So this plate is positive charge, say the charge is plus Q, and this plate minus Q charge. This system is called parallel plate capacitor. Now we calculate the capacitance of this parallel plate capacitor. How to calculate the parallel plate capacitor? First, we see that if this is positively charged and this is negatively charged, then an electric field will be generated between these plates. For positive charge, the electric field is along this direction, and also for this negative charge, electric field along this direction. Therefore, we see that the electric field is from positive to negative direction. Now we have to find out what's the value of this electric field. Here E equal to, say, E1 for positive plate and E2 for negative plate. And this is given by sigma by epsilon naught plus sigma by 2 epsilon naught. And this gives sigma by epsilon naught. Here E is the electric field in the region between two parallel plates, E equal to sigma by epsilon naught. And this is uniform electric field. Within the plate, the field is uniform, but near the edges, the field is somewhat distorted. This plate potential is 0 because it is connected with ground, and say this is potential V. Now we have to calculate the potential difference between this plate, and obviously the potential difference equal to V minus 0, that is V. Now we express this potential in terms of electric field. We know E equal to V by D. Here V is the potential difference and this is the distance between two plates. We have already calculated E equal to sigma by epsilon naught. Therefore, V by D equal to sigma by epsilon naught. Here I forget to mention the value of sigma. What is sigma? That sigma equal to surface charge density. Surface charge density. The surface charge density of positive plate and as well as the negative plate. Now V equal to sigma D by epsilon naught into A. Now we multiply numerator and denominator by a quantity, that is sigma into A, the area, plate area, by epsilon naught into A. Here we multiply numerator and denominator with A. A is the plate area. A equal to plate area. Then sigma into A, charge density into area of the plate, gives the total charge. Q into D by epsilon naught A. Charge Q into D by epsilon naught A. Now we define the capacitance C. C equal to Q by V. This is Q and this is V. Q by V is the capacitance, and we get from this relation this is epsilon naught A by D. This is the expression for capacitance of a parallel plate capacitor, C equal to epsilon naught A by D. Here we consider this region is vacuum, so we include only the constant epsilon naught A. If it is filled with a dielectric constant K, then our electric field will be E equal to sigma by K epsilon naught. Sigma by K epsilon naught, when we fill this region with dielectric medium of constant K, the electric field is equal to sigma by K epsilon naught. Then we get the capacitance C equal to K epsilon naught A upon D. This is our general formula for capacitance of a parallel plate capacitor. Okay? Now I am discussing a problem. Say this is a parallel plate capacitor and the space between two plates is vacuum. The plate separation is D and its capacitance is C. What will happen if the space between two plates is filled with a dielectric medium of constant Q? Then what will be its new capacitance? At first, when the space is dielectric free, the capacitance is given by epsilon naught A by B. But when the space is filled with dielectric, it is epsilon naught A by B. Then C dash equal to K into C. The capacitance is K times of its initial value. Now I will discuss another problem. Here there are two plates separated. One is separate and some region of thickness D1 is filled with dielectric constant of dielectric medium of constant K1, and the remaining is with another dielectric of constant K2. The space between two plates is filled with two types of dielectric medium. One is dielectric constant K1, the thickness is B1, and the another is dielectric constant K2, thickness B2. Then what will be the capacitance of this parallel plate capacitor system? And as before, first we calculate electric field in this region. This is E1 equal to K1 epsilon naught sigma by K1 epsilon naught. E1 equal to sigma by K1 epsilon naught. The electric field in this region, and electric field in this region will be defined, and this will be sigma by K2 epsilon naught. Now we define potential difference between these two plates. This is V1 and this is V2. Then total potential difference V equal to V1 plus V2. What is V1? Here V1 equal to E1 into D, and V2 equal to E2 into D2. E1 D1, that is V1 equal to E1 by D1, and V2 equal to E2 by D2. Then, this is E1 D1 and this is E2 D2. Now V equal to here E1, that is sigma by K1 epsilon naught into D1 plus E2 equal to sigma by K2 epsilon naught into D. And as before, we multiply sigma into A by K1 epsilon naught A into B1 plus sigma into A K2 epsilon naught A into B2. This is the charge in the both plate Q. That is Q D1 by K1 epsilon naught A plus Q D2 by K2 into epsilon naught A. Now Q by V, this is C, capacitance. Here we take common Q by V, this is our capacitance. Then the remaining part 1 by B1 by K1 plus B2 by K2, and this is epsilon naught A. From this relation we get C equal to Q by V equal to epsilon naught A B1 by K1 plus B2 by K2. This is our expression of capacitance. If we take n numbers of dielectric media between two plates, then we can generalize this problem epsilon naught A by di by Ki, here I equal to 1 to n. Okay, this is our discussion for parallel plate capacitor for today. I am giving another example of parallel plate capacitor problem. Say a parallel plate capacitor, plate separation D. The separation between two plates is D. A dielectric slab of thickness, T is inserted between them. Here the situation, two plates, plate separation is D. A dielectric slab of thickness T and dielectric constant say K. Dielectric constant K is inserted between two plates. So this is our dielectric medium. This is K. So the thickness B1 equal to T, and the remaining part is D minus T, and here K equal to 1. Now according to our previous problem, C equal to epsilon naught A by D1 by K1 plus D2 by K2 equal to epsilon naught A, here D equal to T by K plus d2 equal to d minus T and K equal to here 1. Therefore we get C equal to epsilon naught A by D plus T into 1 by K minus 1. Or epsilon naught A D minus T into 1 minus 1 by K. This is our required capacitance of the given configuration. Okay, and this is all about parallel plate capacitor. In our next class we discuss spherical capacitor and cylindrical capacitor, and next we discuss about distribution of charges between two capacitors. Okay, tata, bye bye.